Ok. Muy bien. Buenas tardes a todos. Nuevamente nos reunimos para iniciar este cuarto seminario de la Sociedad Argentina de Espectrometría de Masa. La charla del día de la fecha tenemos el gusto de que sea moderada por Tascón, de la Universidad Nacional de San Martín, quien estará presentando al doctor Fabio Augusto de la Universidad de Campinas, Brasil. Por favor, Marcos.
Hola, gracias Soledad. Fabio, I will introduce you in Spanish first, and then I'm going to moderate in English.
Sure.
Bien. Hoy, bueno, tenemos la suerte de ver una disertación del profesor doctor Fabio Augusto. Y, a ver, para introducir algunos de los logros de él, él es graduado y doctorado en Ciencias Químicas por la Universidad Estadual de Campinas. Entre los años 1999 y 2000 realizó una estancia postdoctoral en la Universidad de Waterloo, en Canadá, en el grupo del profesor Janusz Pawlicin. En 2015 ocupó la cátedra Joliot para investigadores extranjeros en la Escuela Superior de Física y Química Industrial en París, Francia. Actualmente él es profesor titular del Departamento de Química de la Universidad de Campinas. Es especialista en el área de separaciones analíticas, siendo sus líneas de investigación el desarrollo de instrumentación de cromatografía gaseosa bidimensional, combinando herramientas como microtécnicas de extracción y quimiometría aplicada a la química bioanalítica, metabolómica, petroleómica, análisis forense de alimentos y bebidas, entre otras disciplinas. Además, me gustaría resaltar que el doctor Fabio Augusto tiene aproximadamente 130 publicaciones internacionales con más de 3.500 citas, obteniendo un índice H de acuerdo al portal de Scopus de aproximadamente 32, que obviamente esto siempre varía dependiendo del portal. Thank you very much for being here, Fabio, and it's all yours.
Thank you. First of all, I would like to thank very much the Argentinian Society for Mass Spectrometry, Professor Soledad, for the invitation, for the opportunity to be here, not being here, fortunately. I would like to be in Buenos Aires right now. You bet it. I love Argentina. Every time I can, I go there. It's a place I really like. Thank you, Professor Marcos, for the introduction. And well, I would like to talk a bit for you about our recent work here in Campinas. As Professor Marcos mentioned it, our specialty or line of research is focused on sample preparation methods, especially microextraction methods, and separation science, mostly comprehensive two-dimensional gas chromatography. And most of the results we're going to show here for you comes from the combination between them. Most of my slides are in English, and I believe it's better speaking English here. My perhaps Portuguese is not going to be so good, and for comprehension, and my Spanish is limited to ordering food in restaurants, so it would not be a good idea. Most of the slides are in English, 2 or 3 initial slides are in Portuguese because they are from class. Well, the title of my presentation is Headspace Solid Phase Microextraction Applied to Analysis of Compounds with Low Volatility. As is written here, as mentioned, my name is Fabio Augusto from the State University of Campinas, UNICAMP, which is in Campinas, state of São Paulo, circa 100 kilometers northwest from the city of São Paulo, 1 million and a few more inhabitants, a large city. And I'm also attached to the National Institute of Science and Technology of Bioanalytics, which is a network of researchers funded by the National Research Council of Brazil. Well, first, since the attendance is made by a huge variety of people. Most people probably have no intimacy, no knowledge, deep knowledge on solid phase microextraction. We'll talk about this technique. Solid phase microextraction, as PME from English, is not a technique, it's a group of techniques where the extraction is performed by a thin film of a non-fluid, not necessarily solid, as the name says, but non-fluid extracting phase, which can be, of course, a solid, such as active charcoal, polystyrene, benzene, resins, and so forth, or a polymer, which is mechanically is a solid, but that works, that behaves like a liquid solvent, such as silicon, polymethylsiloxane, where the extraction mechanism is partition, that the analytes are extracted by partition. They are extracted to a solution in silicon. So you have a very thin film of either a solid or a polymer, which is immobilized over an adequate surface. And this device is exposed to your sample. Analytes from the sample distribute between the phase present, the extracting phase, the matrix phase, head phase, and so forth, and you isolate them. There are several different formats of solid phase microextraction. You can immobilize the extracting phase over a fiber, which is the more usual format, the most popular format. Use directly as a thin film, a free thin film. You're exposed to the sample. You can put your phase over a rotating disc, over a disc, which is attached to a magnet, put in the bottom of a flask and rotated by magnetic steerers. This is a variant that was developed in Chile by Professor Pablo Richter. Over a steer bar, over suspended particles, what those have in common? Thin films over a surface which is exposed to your sample, and extraction is performed over them. Also, you can use the hollow tubes. You can coat the inner walls of hollow tubes, flow your sample through the tubes, and perform extraction over the walls of this tube, or pack your tubes with particles or fibers or monolites, using needles as support, pipette tips. There are several formats, different formats which we have in common. Small volumes of thin films of sorbents. You perform quantitative but non-exhaustive extraction. You expose those to the sample. A quantity of analytes proportional to the concentration is extracted, but not necessarily 100% of the analytes contained in the sample. It's an equilibrium-based technique. I'm not going to further details. There are enough literature on the topic we can recommend, but it's necessary, I believe, to introduce this. Well, which is common to all those different formats of solid phase microextraction. Some are commercially available, others are only lab-made prototypes, use microvolumes of extracting phase, high phase ratios, high ratios between a sample and extracting phase volume. You have a quantitative extraction, but non-exhaustive. Use thin films of sorbents, which means that you have a fast extraction, usually fast extractions, and the sorbent phase is immobilized over some surfaces. When you do that, you have very easy manipulation. Those are some of the commercial devices available for solid phase microextraction. You fibers, arrows, needles, sewing needles, the so-called twister, which are magnetic steering bars. There are a variety of different forms where you use the commercially available device where thin films of sorbents are immobilized on some surface, and this is used for extraction. But from all points, the more traditional, the more used format for solid phase microextraction. Most people associate solid phase microextraction to the fiber-based solid phase microextraction, which is sold initially by Supelco, but now there are other companies that made those devices available. You have a thin fiber of silica fiber, fused silica fiber, coated with a small thin film absorbent. This is exposed either directly to the sample or its side space. Well, why using fiber-based SPM? Commercial, ready-to-use solid phase microextraction devices have been around since 1994. They are widely accepted, either both by the academy, by the industry. You have even standard methods based on solid phase microextraction, fiber-based devices. They are reliable, consistently manufactured. There's a large user base that I still use and is going to use for a long time, fiber-based solid phase microextraction. So it's interesting to develop applications of, to try to explore the use of this form of solid phase microextraction, which is well known for most people. It's very, very reliable rather than one of the experimental variants. Well, the problem is that fiber-based solid phase microextraction is more suited for GC due to its characteristics. You can use it for direct mass spectrometry, for LC, for lots of different techniques, a sample preparation, lots of different techniques, but it's much more suitable for GC due to its characteristics. And they are very fragile. Solid phase microextraction fibers are very fragile, and they are very, very expensive. A box with 3 fibers costs $250, $300 in US. In Brazil, for example, they cost 10 times more. I believe in Argentina, it's pretty much the same because you have the importation costs, you have the taxes and so forth. So they are very expensive. It's too much money for such a delicate thing. So you have to avoid to damage them at all costs because you lose a lot of money if you break a fiber. So we avoid direct extraction using fiber-based solid phase microextraction. Introduce the fiber in the sample. We try to use wherever possible headspace extraction through the headspace, since most of the species we are going to analyze are analyzable from by GC. GC analyzable species are volatile. You can operate through the headspace. Or for direct extraction, when you insert the fiber in the sample, directly in the sample, only for clean aqueous samples. Well, SPME is a very interesting technique. You want to try for the larger number of samples and analytical problems possible due to their reliability, simplicity, speed. And then we think, why not try to extend the scope of use of the technique for samples that analyze analytical problems which would not be usually would not be considered as feasible by using SPME, such as for analytes with very, very low volatility, non-volatile analytes which this is not something I can analyze using any headspace techniques. This molecule is too heavy, its vapor pressure is too low, and too dirty or solid samples when you cannot stick your fiber inside the sample, but without compromising the simplicity, robustness, the good features of SPME. The solution is simple. You have to couple SPME to other strategies that isolate those analytes with very low vapor pressure from the samples, transfer them to the headspace of this sample, force them to the headspace of these samples, something that is not, it would not be feasible in regular conditions, and then analyze this artificial headspace or a clean aqueous extract. Currently we are studying two different approaches to extend the use of solid phase microextraction to analytes with very, very, very low volatility to solid samples or very dirty samples. Coupling as solid phase microextraction with pressurized subcritical hot water extraction, we transfer the analytes to clean aqueous media before the extraction, and then we extract those very clean, those very favorable aqueous extracts with the solid phase microextraction fiber, and vacuum headspace solid phase microextraction, vacuum assisted solid phase microextraction through the headspace. When we accelerate the transport of very heavy analytes from the matrix to the headspace, and then we stick the fiber to this headspace. Well, the results I'm showing here are intended to be proofs of concept, but they are applied to real samples. The samples results I'm showing here are referred to petroleum reservoir rock core samples, which are limestone or sandstone rocks, which are impregnated with petroleum, with crude oil. Well, what are rock core samples? What are petroleum rock core samples? Well, to show you what are those samples and why it's interesting to use a SPME instead of other techniques to analyze them, I have to discuss a bit about petroleum. Most people know petroleum, but even chemists, most of them really don't remember how petroleum formed. Petroleum is formed from organic matter, from organic matter, from lakes, from rivers, from water environments, not from soil environments, which is deposited as sediments in lakes and sea and marshes, and it's buried by layers of silt, by sands, by other sediments. As it's being buried, pressure, it goes deeper and deeper and deeper, and pressure and temperature increase, and this biological matter is converted into hydrocarbons by a process called diagenesis. So the sediments, lake, sea sediments, marine organisms, so forth, they are compressed in anoxic conditions. The molecules, the organic molecules, the biomolecules are slowly reduced, degraded, and converted to hydrocarbons. There are essentially two types of oil generation environments: marine and fluvial environments. In any case, the sources are zooplankton and algae. Well, you apply pressure to those segments buried inside the soil. Organic matter turns in kerosene, which is the first step of the transformation or gas. After some time, they are converted in heavy hydrocarbons, middle to heavy hydrocarbons that can migrate and be entrapped if they find some non-porous rock, and then you have your oil well. The oil well essentially is the formation where we have porous rock impregnated with oil. Well, how can I determine if a particular oil reservoir has commercial value? From seismic measurement, other type of geological measurements, people know that under the earth, under the soil, on thousands of meters below the soil, there's oil entombed there. How I know it's worth to explore that? People do a type of investigation based on stratigraphic wells. They do well over to 6,000, 7,000 meters under the soil, collect rock samples from there. Then you investigate those rock samples that have organic material impregnated, are potentially from reservoirs. So you have to extract the oil and analyze to check if the oil on that deposit, on that reservoir, is worth to be explored. You can imagine that this is a very, very costly operation. It takes millions of dollars to explore, to drill such wells. Well, how do you analyze those samples? You have to pick the raw rock, crush in piece, ground in those ball mills to find particles, sieve. The standard procedure to analyze the organic content of these rocks involves you transfer to some grams of the rock a paper thimble and extract in a Soxhlet device for 2 or more hours of dichloromethane. So you have the raw organic extract. This extract is not analyzed, directly analyzable by GC, has the raw petroleum on it. You have to remove the so-called asphaltene, which are the resins. You have to discard it or characterize by, if you want. The supernatant, which is the more volatile fractions, the so-called maltine, has to be fractionated in columns like that. The compounds that are more relevant to characterize the oil are the saturated hydrocarbon fraction, which is first fraction you collect on this procedure. You collect aromatics and resin fractions. Then you take this first fraction of this procedure, reconstituted, and then analyzed by GCMS, GCFID, MS, direct MS, several techniques you can use. Those are typical GCMS chromatograms for this extract, this F1, the first fraction of this fractionation extract from petroleums with different characteristics. To characterize the oil, to check its characteristics, to see if it's a valuable oil, you have to look after some biomarkers, some compounds present in trace amounts, which are kind of fossils of biomolecules, residuals of the biomolecules present on the organisms that form that oil, depending on the relative concentrations of those biomarkers. You can have one or other type of oil. Those are some of those biomarkers, such as phytane, pristane, lycopene, cholestane, gamma serene, which is C13 hydrocarbon. Most of those biomarkers are very heavy hydrocarbons, up to C14, and they result from oxythermal degradation of the biomolecules. They are chemical fossils. They are present in trace amounts on these chromatograms, so you have to apply that exhaustive extraction procedure and try to quantitate those species. Well, this procedure is very time consuming. It can take up to 10 days to analyze a single sample. Some of those species are present in nanogram per liter concentrations. You have to use very large amount of solvents, up to half to 1 liter of dichloromethane per sample, fluoxetine, lots of solvents, materials, and depending on the rock, you have to destroy the inorganic fractions for hydrofluoric acid, nitric acid. Sometimes you have to use thin layer chromatography as previous fractioning. These are very outdated, anachronistic approach, but it's the standard for most of the organic geochemical labs. But why not simplify that using solid phase microstructure? Most of the relevant petroleum biomarkers are compounds with high molecular masses, with very, very, very low volatilities, but they have a vapor pressure high enough to analyze them by GC. So if you can analyze a compound by GC, the general rule is you can extract it by some headspace technique. Although for those compounds, this is not usual. Most people would not see those compounds, gamma colestan, gamma seran, etc., as compounds you analyze with any headspace technique, especially headspace solid phase microstructure. So if it's possible, why not replace SOX extraction here by headspace solid phase microstructure? Well, there are two forms of doing that. The first approach we try to use, we've been using it, is combining pressurized hot water extraction to direct solid phase microstructure. First, extract the hydrocarbons from the rock samples using subcritical water at high temperatures, and then stick a fiber on this water extraction, collect the hydrocarbons and analyze it. Why water? Why it's illogical using water for removing hydrocarbons, for example. It's madness, apparently. But at very high temperatures, you can keep the water liquid if you pressurize it. And at a very high temperatures, liquid water can be as hydrophobic as organic solvents. Properties such as permittivity, dielectric constants, etc., for water decrease with the temperature. For example, at 300 degrees, you have to keep the water at very high pressure, for it became liquid. Water has a permittivity lower than acetonitrile and methanol. It's less polar than those compounds. So you can use very hot water, which you can obtain at very high pressure, as an extracting solvent for hydrocarbons, for example. This is relatively simple. Use water extraction. You just have some device to keep the water as liquid at those temperature and pressure, and use it to extract your sample. After a procedure, you have your hydrocarbons, your petroleum hydrocarbons, in a very clean water sample. Then you can stick your fiber inside that water extract, re-extract your hydrocarbons, and analyze them. The experimental setup for pressurized hot water extraction is very simple. Pressurized solvent extraction is a modality of extraction that can be very cumbersome if you use organic solvents, but for water, simple, because you just need a moderate pressure to keep water liquid at very high temperature. 15 bars is enough to keep the water liquid at 200 degrees Celsius. You do not need to have a very strict control of pressure temperature. You need to have a pump to pump the water to a extracting cell. The extracting cell has to be kept on a oven, of course. In the exit of the system, you need a back pressure regulator, some device that keep the pressure of the system behind it. Control it, pass the water at high temperature to your sample, and then collect the extract. The first report on this is very old, 1996. It's not a very new combination, but for some reason, it was abandoned. Not less than 10 papers combining hot water extraction and solid phase microextraction have appeared in the literature, mostly because the first reports deal with PAH, alkyl benzenes, and other compounds, where you really don't need it. You can perform direct solid phase microextraction, then you don't need this hot water thing for that. So those applications are for analytes which other methods are more convenient or simpler. We try to apply this combination for those oil biomarkers in rocks, because for them it's really necessary. You have to use that software thing. But for analysis, we use multidimensional gas chromatography, which I'm not going to enter into detail here. It's a technique that has a very, very high separation power, and you do not need to use those pre-fractionation schemes with several columns before the chromatographic separation. We can inject directly the sample of no further preparation. Well, this is our device for this technique. We use a very old syringe pump, LC syringe pump, to impulse the water through the system. We use a very old GC oven to keep the temperature of the system. This is a GC oven that was stored to be discarded, to take heat for using that. There's a heating coil here inside. A sample cell is a stainless steel sample cell, just a tube, the two nuts to keep the sample inside. A back pressure regulator here, and the flask to collect your sample. Put your sample here. We ground the sample to very small particles. We mix them with glass beads, 1 to 5 ratio. We cannot put the sample inside the cell directly and put pressurized water because the particles are too fine. And if you put pressurized water over it, it turns it into a cake, something that is almost not permeable. So you have to disperse it in saline or other device. In this case, we use glass pads to avoid the sample to be very packed. We put 1.2 grams of this sample beds mix. We pass water for some time at temperatures and pressure that we optimize, and we'll describe the optimization further. We collect 16 mL of extract, transfer 15 mL to a vial, and extract then with this triple fiber, PDMS, carboxyl-divinylbenzene, SPM fiber. A fiber, this is a so-called triple fiber, so a fiber commercialized by Supelco that has those 3 sorbents, 2 solids and one polymer. It's very efficient for a series of analytes. 15 minutes extraction, 60 degrees, and then we chromatograph it. Well, to optimize the extraction conditions, we use multivariate procedures. Everything we do in our lab is optimized through multivariate chemometric strategies because there are too many variables to optimize, especially on microextraction techniques. It's almost impossible to determine the optimum performance conditions using univariate procedures for optimization a condition at a time. So we have to use those multivariate approaches. It's much more intelligent to use that. We optimize the water flow rate, the water temperature, and the pressure of the system in terms of reduced pressure, not absolute pressure. Reduced pressure has a relationship between the pressure and the vapor pressure of water at the temperature of that particular experiment, using a multivariate approach called Dollard matrix optimization. We combine the conditions in 25 sets. We run 25 experiments in different conditions. The response optimizes the total peak area, the sum of peak areas of all analytes. The best conditions, we fit the response over surface and check which are the optimum, the maximum of those surface. The best fit was a quadratic surface, and then we found the optimum water flow and temperature are 2.5 mL per minute, 275 degrees, and the optimum pressure 150 times the vapor pressure of water, which is 90 bars of those conditions. Those are the response surface for the variables. As you see, that it's a very complex behavior. Well, these are pictures of the sequential extracts we obtained. We collected portions of 4 mils sequentially, then combined them from a rock sample for 4.5% of hydrocarbons. You see, we can really isolate by the color of the extract. We can really isolate efficiently the material inside. This is a GCGC chromatogram, single ion monitoring chromatogram for GCGC-MS. We locked the mass spectrometer on the fragment 91 Daltons, which corresponds, as you know, to the characteristic fragments of aromatic compounds. Each dot here represents a different compound, aromatic compound in this case. So you can see we can isolate the hundreds of different compounds. In this case, only aromatics are seen. This is toluene benzene here, naphthalene, and so forth. I'm not going into detail about this. We found this combination is very efficient for highly hydrophobic. It's not very efficient for highly hydrophobic species such as saturated hydrocarbons. Obviously, is better for aromatic compounds and other less hydrophobic compounds as well are being used. And it seems to be an excellent alternative for these compounds, but not for general and target analysis. Right now, we are studying combinations of ethanol and water mixtures, blends of methanol and water. The results are very promising, and applying it to other compounds, other samples, such as plant samples and so forth, with very interesting results. But of course, water as hot water, supercritical water is much more adequate for aromatics. Well, the second approach we used was vacuum headspace solid phase microstress. Solid phase microstress sometimes is used for headspace extraction. You put your sample in a vial, lock it, expose your fiber to the headspace of that sample, and extract volatile compounds. The problem for extraction of compounds with very, very, very low volatility, such as those biomarkers, is that you can extract them, but the process would be very slow, to take a very, very long time because the vapor pressure is too slow. Years ago, especially Professor Psilaxis in Crete, Professor Elia Psilaxis in Polytechnic Institute of Crete, started to ponder. Well, the limiting step on headspace solid phase microextraction to reach the equilibration is the diffusion of the analytes through the so-called static diffusion boundary layers that exist between the different phases on the system, between the liquids, in case you use a liquid sample, and the headspace, between the headspace and extracting phase on the fiber. And they suppose that if you reduce the pressure, if you do some effort to accelerate this mass transfer, especially for compounds with very low volatilities, for example, very low Henry law constants, they could accelerate the overall process. How to speed up the process? How to speed up the mass transfer process to extend the technique for very, very heavy molecules? You can increase the temperature of operation, which is limited, but you can damage your fiber. You can have effects on the equilibration position of the structural equilibrium process. It's limited, the increase. And also you can perform your extraction under very low pressure, the vacuum. If you perform your extraction under vacuum conditions, the process of mass transfer from the sample to the fiber is very, very accelerated. And they demonstrated that in practice in 2012, the paper is here, no? That under very low pressure conditions, extraction of semi-volatile compounds, Henry-Law constants between 1 to 10 to 1 times 10⁻³ mole Pascal cubic meters is extremely accelerated. Well, until 2021, there are around 30 papers on this type of combination, extraction of headspace of samples with solid phase microextraction under vacuum is underexplored yet. And also most of the applications refer to semi-volatile analysis, where you can use other combinations of solid phase microextraction and headspace procedures to work. In this work, we try to apply vacuum headspace solid microextraction to those oil rock biomarkers, which have a very, 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 very low volatility, 10 to -8 to -10 mole Pascal cubic meters Henry-Law constants, and directly on the solid markets. This work has been already published. We published it in a new journal, Advances in Sample Preparation. It's a Elsevier journal. The DOI of the paper is here. It's an open access journal. Since the journal started some months ago, up to July 2022, publication here will be waived from publication taxes. So if someone works with sample preparation and to submit the paper there, you are not going to pay. I'm one of the editors. That's why the publicity. Well, the procedure was very simple here. We enclosed the solid sample in a vial with septa, pre-drilled thermogreen septa in the modified mini-inert valves. Mini-inert valves are valves for headspace sampling. Professor Elia Psilax donated that for us, but it's very simple to prepare it. We evacuate it with a low-cost pump. It's a GM 0.5 pump. It's a pump that costs less than $500. It's a very simple Chinese-made pump. The pressure goes to 200 millibars. It's not a very intensive vacuum. Then we transfer the vial to a heated block at determined temperature, keep some minutes there for equilibration. Then we expose the fiber coated with 7 micrometers PDMS, polymethylsiloxane, to the headspace, waited for some minutes, and then we picked up the sample and analyzed by GCMS. We use this sample, which is not very used because it's too thin, because it stands very high temperatures, and in this case we need to use very high temperatures. Again, we used multivariate optimization of the extraction conditions. We optimize sample mass, the sample headspace per extraction time, extraction temperature, extraction time, and we optimize not the total peak area for scan chromatogram, but we locked the mass spectrum, the MS detector on the fragment 217, single eye monitoring chromatogram. This corresponds to the fragment characteristic of steranes, which is a class of biomarkers very relevant to oil samples. Performed also 25 experiments, and we found those are the optimal conditions: 15 minutes sample headspace optimization, 15 minutes extraction, sample at 250 degrees. The mass of sample was not relevant to the model, so you can use any sample. We fix it on 160 milligrams, which compares very well to the 10-gram sample. Imagine the cost of those samples. Those are the response surface we obtained, and these are the results. In this case, we used regular unidimensional gas chromatography, SARA, saturated asphaltene resins, saturated aromatic resins and asphaltenes. It's the name of that fractionation and Soxhlet protocol I showed to you. Bottom blue is the chromatogram for sample obtained with the conventional Soxhlet procedure. The upper in black, the chromatogram using vacuum headspace solid phase microextraction. Of course, we collect with more efficiency in the headspace, the less volcanic, the more volatile species. Those are chromatograms, single element chromatograms corresponding to hopanes and steranes. This is the fragment monitoring for hopanes, 191 Daltons. You see the structure of the hopanes here is very complex. It's related to biomolecules present on the organisms that originate the oil. Steranes, this is the fragment we monitor 217 Daltons. Those are the hydrocarbons, the comparison, the chromatograms, comparison of the chromatograms between the two techniques. As you see, vacuum headspace solid phase microextraction is completely similar to the Soxhlet extraction procedure. Of course, some of the very heavy compounds are lost, but this would be expected. It's very difficult to run a direct comparison of quantitative performance between the two methods. There are no standard samples of oil porter rocks. You can spike the oil on the rocks, but it's not realistic. It's not easy. That what we do to compare both techniques is compare signal to noise ratio in chromatograms of vacuum headspace solid phase microextraction analysis and Soxhlet analysis, and see what happens. As we see, this is the relationship between signal to noise ratios for peaks in vacuum and Soxhlet extraction in function of the rotation index of the peak, which is the length of the hydrocarbon chain. As you increase the hydrocarbon chain, of course, solid phase microextraction headspace solid phase microextraction becomes less favorable. But remember that we are replacing a technique that it takes 10 days to obtain the results. This is for hydrocarbons. For other compounds, there is not such a clear relationship, but the structures are very varied. So in homologous series, it may be a tendency. Efficiency of the vacuum headspace solid phase microextraction seems to be related directly to the vapor pressure of the compound, which is a function of the length of the molecule. And in this case, we used a very thin, the superior sensitivity. If you use other fibers, such as 100 micrometers PDMS, divinylbenzene PDMS 65 micrometers fiber, we would have very, very higher sensitivities. But our focus was not sensitivity here, but robustness. So we use the PDMS 7 micrometers fiber. And as for the quantitative validation, we performed a sort of quantitative validation for this procedure. The problem is we don't have standard samples. We have no amounts of each marker. So what we did, we take a sample, selected a sample with some content of organ carbon, 4.3% of total organ carbon, mixed with rock exemplars of oil. We mixed no amounts of each rock and extracted to simulate rocks of different amounts of extractable oil. And it seems that vacuum headspace solid phase microextraction is indeed a quantitative approach. You can quantitate in a limited range the biomarkers in the rocks. Well, to conclude this, when coupled to subcritical water extraction, you can have very relatively good recovery and moderate selectivity for moderately polar and hydrophobic compounds. But for non-polar, highly hydrophobic species, the efficiency is not as good as expected, as it would be expected, of course. Right now, we have very good results of water and organic modifiers for these samples, and we've been applying, for example, for plant materials, and the results are very interesting. As vacuum headspace solid phase microextraction, we have very, very good recovery for all compounds, especially for compounds of very high boiling points for low vapor pressures, such as C30 hydrocarbons. Where we have 4 times 10 to minus 8 microbars as vapor pressure, and using only moderate vacuum, 200 millibars, 0.2 atmospheres. This is similar to the exhaustive procedure where you need to use 10, 12, 15 days of operation. There are some theoretical models on vacuum headspace solar extraction, which are based on in-law constants, but they not apply to these samples here. We are trying to develop a theoretical model for them. And for both the combinations, there are vast room for development for specific developments. Well, this is what I would like to show you. Most of this work was performed by my PhD student, Paulo, and my colleague, Professor Paulo Rosa, is a specialist on supercritical fluids and pressurized fluids, collaborate on most of this work as co-supervisor for Petroleum. Most of my work was funded by CNPq, which is the National Research Funding Agency in Brazil, CAPES, which is the agency that funds scholarship for grad students, São Paulo State Research Foundation, FAPESP, FINEP, which is a federal government organ that provides funding for companies, and especially from Petrobras, which is the national Brazilian oil company. They provided a lot of funding to us. Well, that's what we would like to present you. Thank you again for your attention. Thank you for the invitation, and I'm at your disposal for any comments or questions. If you want to question me in Spanish, it's okay. I'll try to answer. Thank you.
Thank you, Fabio. Virtual clap. I have a few questions from YouTube. Let me translate it first. Well, the first question is says the fibers have different colors on the. I think the plastic half that the sepulchral fibers have. I would like to know what analytes can be extracted for the pink and light blue caps of the fibers.
Oh, those colors are a code for the supplier. The different colors are used for different coatings. As far as I remember, I don't have all color codes by memory. As far as I remember, the pink is for PDMS DVB coating, and the blue is for 7 micrometers PDMS. PDMS DVB is more selective towards more hydrophobic compounds, and it's more efficient. Overall, is more efficient because you have a small fraction of a solid adsorbent. Solid adsorbents tend to be more efficient. And for coatings which are polymeric, so PDMS, of course, PDMS is non-polar, so you have a very high affinity for non-polar hydrophobic compounds, and depending on the coating thickness, you have more or less efficiency. I don't have the table here, and I really don't remember all colors. This one, red one, is for 100 PDMS coating. This is for carboxyl PDMS, and this is PDMS DVB, as far as I know. That depends on the composition. This is and this is for Supelco. Other suppliers have different color codes for their fibers.
I think for this case, if they can go to the Sigma Aldrich website, they can find the
Sigma Aldrich has on the website. They have the documentation that describes all these color codes.
The prices as well.
The prices. But the problem for us in Brazil, Argentina, is that price is kind of science fiction. No? You cannot purchase by that price. You have to pay much more for those fibers. Even US, the amount that they ask for the fibers is considered exaggerated. Right now, there are several other suppliers, minor suppliers. There's a guy in China that is making those fibers for, I guess, 40 to 50% of the price that supplies it. The problem is distribution. It's hard to purchase for him because he doesn't have an international network of distribution. There's another company, I guess, in Germany that prepares it. But the problem is those are small companies. They don't have a very good distribution networks. You can prepare your fibers, but it's not recommended.
Yes. Okay, I have another question. What is what is the optimum pressure of water to do the extractions? And if you can add sodium chloride to improve the volatility.
Oh yeah, I stopped to share the screen. Sorry, I will share again. Just a second.
You can try to share again, Fabio.
Yeah, I will. Just a second. Just let me find the program here. Just a second. Here. The pressure for water. Let me go in the slide. Just a second. Well, the optimum pressure for the extraction was 90 bars, which in atmospheres is more or less 90 atmospheres. This was the optimum pressure. We checked conditions from 100 to 200 to 250 to 350 bars in the optimization procedure, but the optimum was 90 bars. Or the optimum was 90 bars, which is doable. It's not using a syringe pump. You can keep your fluid on that pressure without problems. That's the good thing using water. Other solvents would demand very high pressures to stay liquid at that temperature. That's it.
Okay, I think I don't know if sorry. They also asked for the sodium chloride addition.
The sodium chloride.
Well, it can either improve or not the volatility.
In this case, no, because we use a solid sample. We are using solid samples. If we were using aqueous samples, yes, it would improve the efficiency. But in this case, we are extracting directly from the powdered rock. Some works from Professor Psilax, most of the works of Professor Psilax you are performing on aqua samples. On those cases, she used, in some cases, sodium chloride to dislocate the equilibrium. It makes sense, but in our case, no. If we added solid sodium chloride there would be no effect, because sodium chloride would stay in solid state. The sample is in solid state. There is no solid state. It's not a solution. And if we add water there, we would have problems with the evaporation of water, reducing breaking the vacuum, making the vacuum being more difficult to apply. So in this case, we don't use sodium chloride as opposed in most of the operations using headspace solid phase microstructure.
Okay, thanks. Have another one, a third one. How much is the level of vacuum reach in the vial when you do this VAC HSSPME?
Let's go there. In our case, we lock the pump at the maximum vacuum obtainable, which is 200 millibars. This is 0.2 atmospheres. It's not a very, very deep vacuum. We are trying to obtain a better pump, but the problem is if you try to use to apply less pressure here, this interface here would not stand such a very low pressure. But 200 millibars is 0.2 atmospheres. It's low enough, the pressure low enough to result in a very, very pronounced acceleration of the mass transfer process. If we reduce more, we're going to check it. Perhaps the difficulty on manipulate such low pressure environment would not result in such a very high improvement. For example, a lower pressure would demand special vials, thick glass walls, because we can explode the vial can improve with the pressure. We need to use better seal here, and the improvement would not be that. So 200 millibars, which is provided for this pump. This is almost a toy pump. I don't have it here, the lab is in another building. It's a very cheap pump. It's not a very sophisticated. So it was really surprising. We could get such good results with this rudimentary. We started, well, let's try to play a bit with that. Then we will obtain a better pump. This device here provided us a very good results. Not very low pressure. 0.2 atmosphere is not high vacuum.
Okay, I think Soledad raised her hand, so I imagine she has a question.
Yes, I would like to ask you about how long the vacuum procedure normally takes.
Well, in this case, to reach the vacuum, I guess in 2 or 3 minutes, after we apply the vacuum, we use a needle, microsyringe needle here to connect to the vial. 2 or 3 minutes, it reached the lowest value possible. And after evacuating the vial, which we found is that in 15 minutes of pre-extraction equilibration, we reached the maximum of extraction efficiency. So 15 minutes equilibration under vacuum, 15 minutes extraction was okay here. To go from atmospheric pressure to the operational pressure, in 2 or 3 minutes, we reached that pressure with this pump. I believe that other more sophisticated pumps would be more efficient than that, but that was okay. Nothing that was that bothered us, that implied is more operational time and slower analysis.
Thank you, Fabio.
One question, Fabio, that I've read the paper a month ago, I think, was released. And from an experimental point of view, you do, it's just a vacuum hose with a syringe needle, right? Or
yeah, just a vacuum hose, just a silicone tube, a thick layer silicone tube, and the tip we put a piece of septum and stick the needle there, and then we can introduce it in the vial to make happen. That's very simple. There's a needle from those replaceable needle micro syringes. We have some there. Use one for that.
Great.
Very simple. Very simple.
And is there any way to check beyond the kinetic of extraction that you have reached some level of vacuum from experimentally, or
to check if the vacuum was well, the pump has a dial, the pump has a manometer, so we see there. Of course, after some time, when you put your sample inside the heating block, volatilization may reduce the vacuum, but for the same sample, we think that this is repeatable, comparable. And even if you use other samples, there are trace amounts of oil. In this case, we select a sample with a very large oil concentration to be sure of it. But for most of the samples, the amount of oil is very, very small. And also, now you are trying to use it for sample materials, dry leaves and stuff like that. In this case, there is no effect at all, and the temperature is much lower, right? Of course, we're going to the other direction. Instead of using cooling the material, because those are biomolecules. Well, let's see if we can manipulate labile, easily oxidable molecules using vacuum, so you don't need to heat up as you would heat on standard solid phase microsuppression.
Great. Thank you. I don't know if I think in the chat there is no more questions from YouTube.
No other questions from YouTube, and I told people there that if they have some questions later, we can forward the questions to Dr. Augusto in a different situation, in different occasion. Thank you.
Great.
Okay. Well, in the name of the Sociedad Argentina de Espectrometría de Masa, thank you so much, Fabio, for giving us this very, very interesting talk. And it has been a pleasure. Thank you also to Marcos for moderating your presentation. And we appreciate all the audience who joined us today here in the Zoom and also on YouTube. And we are expecting all of you for our next week. Dr. Timothy Garrett will be giving us his conference about metabolomics and mass spectrometry. Well, thank you all for being with us today, and we hope to see you next week.
Thank you.
Thank you
for the
Thank you,
invitation,
Paulo.
for the opportunity.
Thank you so much.
Nice talk. Thank you.